In this video, we're going to talk about electrolytic cells. And remember, electrolytic cells were the opposite of our galvanic cells, right? In a galvanic cell, we had a spontaneous chemical reaction that produced or resulted in electric current. Here, we're going to have an electric current that's used to drive a non-spontaneous chemical reaction. So electrolytic cells. An electric current is used to drive a non-spontaneous reaction. So again, it's the reverse process, right? Of a galvanic cell. Right? In a galvanic cell, we're going to convert chemical energy to electrical energy. Right? It's going to have a positive cell potential and a negative free energy change. And it's going to push our reactions towards equilibrium. Remember, spontaneous reactions always go towards equilibrium. Our electrolytic cell then it's going to convert electrical energy to chemical energy. We're going to have a negative cell potential, a positive free energy change, and it pushes our reactions away from equilibrium. So we're going to look at an example of an electrolytic cell here. And the one we're going to do is going to be the electrolysis. Electrolysis, by the way, is just the name for that process. So the name of the reactions are going to be electrolysis, or the process of molten sodium chloride. So essentially what that means is liquid sodium chloride. We're used to seeing it as aqueous ions. We can have molten sodium chloride. So our reaction for this one, I'm going to have 2 sodium ions, and they're going to be liquid, plus 2 chloride, going to 2 sodium, plus chlorine gas. And this is balanced for us already. You could check your number of atoms and your net charge, and it is going to be balanced. Our 2 half cells are going to be my 2 chlorine going to chlorine gas, and then 2 electrons. Electrons here are my product, so this is my oxidation. And in our electrolytic cells, oxidation is still going to occur at the anode. My second half cell is the 2 sodium ions going to 2 sodium. And then to balance our charge, I would have 2 electrons on this side. If you were to look this up, because these are all divisible by 2, right? I have a 2 here and a 2 here and a 2 here. If we were to look up our table of standard reduction potentials, you're actually going to see those as 1s. The reason it's multiplied by 2 is to get our electron counts equal, But again, if you look up your cell potentials using your standard reduction potential table, it is going to look like this instead of with the twos above. Which is actually, I'm glad I brought that up. I don't know if I've mentioned this before. Your cell potentials are independent of the coefficients. So like if I look up the value for this one, which I was going to write down anyway, so my reduction half reaction cell potential is, I'm just going to move it over here because I'm not going to have room, is a negative 2.71 volts. And when you look that up, it's going to be with this reaction. When you multiply it by 2, it does not change this number at all. So our cell potentials do not matter as far as, or we should say, yeah, our cell potential, like the value, does not matter what the coefficients are. So multiply by 2, by 10, cut it in half, it doesn't matter, as long as you have sodium plus liquid going to sodium liquid. This is its cell potential. Let's write down this one here. This one is a negative 1.358 volts. And again, this one's actually going to be written in the table in the other direction, but because it's our oxidation, we reversed it. This here, I didn't finish writing it, is my cathode. Our cathode is still going to be the electrode where our reduction occurs. And then if we were to add those two values together, right, my standard cell potential is going to be the negative 1.358 volts plus our negative 2.71 volts. It actually comes out to be a negative 4.07 volts. And the reason I'm doing that is I just want to make a point here of that negative sign, right? Because we're looking at an electrolytic cell, we're going to have a negative cell potential. This is a non-spontaneous reaction. So again, just to not get these mixed up, it's the reverse of our galvanic cell, right? When we were doing our galvanic cell, we wanted a positive cell potential. Now we're doing electrolytic cells, we want it to be a negative value. So just be really careful. All the ones we've been doing up to this point, we want positive values. Here we're going to switch the sign on the one that we want so that it comes out negative. You're going to always switch the sign on your oxidation. So we're going to sketch a little picture of this. And because it's a non-spontaneous reaction, we're going to actually have to hook it to a power source. So when we were doing our galvanic cells, the electrons went spontaneously from the anode to the cathode. Here, we need to pull them. So we actually have to hook it to a power source. So when we sketch our picture here, and I'm going to have my two electrodes. And we do have an electrolytic solution in here. And then instead of just hooking the wire, I'm going to erase this here. Instead of doing this, I actually have to have a power source in the middle. So I'm going to draw a battery. This is a little picture of a battery, but just any sort of direct current. So this is going to go here. That's drawn pretty poorly. And then this is going to come here. So I am going to put my anode compartment on the side the way that I usually do, on the left. And then this is going to be my cathode over here. Our electrons are still going to go from my anode to my cathode. So our electrons are being pulled by that battery and then pushed towards that cathode. Again, they're not going spontaneously. It's that power source in the middle that's pulling those electrons from my anode and pushing them towards my cathode. We can actually, let's write that down because that's important to note. So leave a little space because we are going to add some things here still. But the battery, or again, any other direct current, so any sort of power source here, it's going to serve as an electron pump. and pulls the electrons from the anode and pushes them towards the cathode. Right? Again, it's non-spontaneous, so we need that power source, right? We need that electric energy to drive this reaction. So my anode, we said, was still our oxidation, so I'm just going to write this reaction down here. My cathode is still my reduction. So on this side, I have my 2-chlorine going to chlorine gas plus my 2 electrons. And then on this side, my 2 electrons are being added to sodium ions to produce sodium. So I have chlorine going this way and then sodium going this way. So our anode is still our oxidation, but we're actually going to make it our positive electrode. In our galvanic cell, it was actually our negative electrode, and it's because the electrons are being pulled from it. And then my cathode is still my reduction, but it's my negative electrode. So let's write that down too. So anode, right? It's still my oxidation, but it's going to be our positive electrode. Right? Electrons are pulled from it. In our galvanic cell, we can add that here for contrast, right? It was our negative, and that was because it supplied the electrons. Our cathode then, it's still the reduction, but it's going to be our negative electrode. Right? In our galvanic cell, it was the positive electrode, because it consumes the electrons. So our positive electrode up here is going to attract my chlorine. So my positive electrode is attracting my chlorine. And then my negative electrode, my cathode, is attracting my sodium ions. Another example, and this time we're going to use calcium chloride. So molten calcium chloride again. Our anode half reaction is actually going to be the same as it was with our sodium chloride example. So 2 chloride and that's going to chlorine gas plus my 2 electrons, right? So that's my oxidation. We're losing electrons, we're producing electrons. And then our cathode, I'm going to have calcium ions this time. We're going to gain electrons and we're going to produce calcium. And then adding these together to get our net equation, right? I have 2 electrons on both of them, so those are going to cancel out. And I'm going to have my 2 chloride plus my calcium going to calcium plus chlorine. That's supposed to be an L. So a different twist on this one, what we're going to do is we're going to actually calculate the mass of chlorine gas that we're producing, right? That's one of our products. And if we know the current and we know the time that that current is run for, we can actually calculate its mass. So again, our current was one of our fundamental SI units. Its abbreviation was a capital, sorry, its abbreviation, its unit was an amp, whose abbreviation is capital A. And if we were to define a current, it's the charge. The unit for charge is a capital C for Coulomb. The C doesn't stand for charge, the C stands for Coulomb, so just be careful there. And then per time. And its unit was seconds. So my charge per time is my current. We also are going to use the Faraday Constant, F, and we're going to use that essentially as a conversion factor. So I know that it's 96,500 coulombs for every mole of electrons. So if we know our current, and we know the time, right, we can calculate the number of coulombs. And then I'll use the Faraday constant as our conversion factor between coulombs and then moles of electrons. For moles of electrons, we can get moles of chlorine, and then we can get the mass of chlorine using its molar mass. So that's the plan. So our actual problem here is, what is the mass of chlorine produced? When a current of 45.2, it's supposed to be a 5, amps is passed through our calcium chloride cell, sorry, not doing so well here, for 1.5 hours. So 1.50 hours. So again, we're just going to use this, right, to calculate the number of coulombs that I have. Because my time here is in seconds, I do need to convert hours to seconds. So let's do that first. I have 1.50 hours. I know that there's 60 minutes in 1 hour and 60 seconds in 1 minute. So that tells me that 1 hour is 3,600 seconds. So I'm going to grab my calculator here. And I got 5.40 times 10 to the third seconds. So we're just going to then plug in my amps for my current here. We're going to plug in this. We're going to solve for our charge. So 45.2 amps gives me my charge, that's what we're solving for, over 5.40 times 10 to the third seconds. So solving for charge, just grabbing my calculator again. I get big number here. I'm going to write down all the digits and then we'll round after. So I have 2044 and 80 coulombs, right? That's what that capital C stood for. That was my unit. So now that we have the number of coulombs, it's really just going to be dimensional analysis. Again, we're going to use our Faraday constant as our conversion factor, right, between coulombs and every mole of electrons. So I'm going to start out with this number, and then we'll just start doing our dimensional analysis. Oh, significant figures. I said I would round after. I'm just going to underline this to keep track of it. I do want 3 significant digits in my answer. So I have 3 there, I have 3 here, so I'm just going to underline that to keep track of it. If you wanted to round after each step, that's perfectly fine. And you can just put a C, you don't have to write it out. I just don't want you to think that it stands for charge, so I'm going to write it out. Coulombs is the unit of charge, so my charge is 244,080 coulombs. And then using my Faraday constant, because coulombs are on the top, right, and that conversion factor, and coulombs are on the top here, I need to divide, right? Remember, for our units to cancel when we're doing dimensional analysis, they need to be opposite of each other. So coulombs for every mole of electrons, and then these guys are going to cancel. So I now have moles of electrons on the top, right? To get those to cancel, right, because we're trying to get to mass of chlorine, I need to have moles of electrons on the bottom. So let's scroll back up to our equation here. And I know for every 1 mole of chlorine, right, there's a coefficient of 1 here. For every 1 mole of chlorine gas, I have 2 moles of electrons. So we're going to use that as our conversion factor. So 2 moles of electrons for every 1 mole of chlorine gas, and the moles of electrons now cancel. Once I have moles, grams is easy. We just use our molar mass. So my molar mass for chlorine, there's 2 chlorine atoms, 35.45 times 2. That gives me 70.90 grams per mole. Moles cancel, and we're going to be left with grams of chlorine. So typing all of this into my calculator, I'm going to end up with 89.7. Remember, we want 3 significant digits. I did have this underlined to keep track of it. Grams of chlorine. If we were to think back to a galvanic cell, our electrodes, and I don't remember if I had mentioned this previously, but they do gain or lose mass during the reactions. So this calculation of mass isn't necessarily unique to electrolytic cells. Let's actually take a look. Let's look back at galvanic, right? So our electrodes do gain, lose mass. Unless, of course, the electrode is platinum, right? It's something that's not actually involved in my reaction. But if your electrode is one of the metals that's part of your half reactions, they are going to gain or lose mass. So looking at our galvanic cell, and I'm just going to use the zinc and copper example that we had previously, and I'm just going to do a really quick rough sketch here of a galvanic cell. I have my electrodes, they're connected by a wire, right? My electrons are moving across the wire in this direction, right? This is my anode over here. This is my cathode. Remember, my anode was my negative electrode in a galvanic cell, positive in electrolytic, and then my cathode here is my positive electrode in our galvanic cell. And then if we're going to use that zinc example, zinc and copper example from a previous video, I have zinc solid going to zinc 2 plus 2 electrons, so that's my oxidation. And then I have copper ions plus 2 electrons going to copper solid. So this electrode here is copper. This electrode here is zinc. And if we look at our half reactions, I am losing zinc solid, right? Zinc solid is being converted to zinc with a positive charge. We noticed that when we were looking at the corrosion of iron, right? As iron solid was oxidized, we got pits in the metal. Kind of a very similar thing here. This electrode is actually going to lose mass because the solid is converted to ions, and then the ions are just given off into our solution. So I end up with zinc 2+ building up in this solution. Copper, I'm forming copper. So it's actually going to gain mass. These copper 2+ ions are being attracted towards that electrode and being converted to copper. So zinc here loses mass. And maybe we should write that up by the electrode. Oops, meant an eraser, right? It's the anode. It's going to lose mass. And my cathode is going to gain mass.